So this is from module 11.2, proving figures are similar using transformations. So we've talked about dilations, but we're kind of going back to the conversation of transformations and then leading into similarity. So our essential question is how can similarity transformations be used to show two figures are similar? Now, our shortest answer is basically if a sequence of similarity transformations can be shown to map one figure to another, then the figures are similar. Now, please note one thing: similar, okay, similar is not the same as congruent. Okay, so remember, congruent means that all the parts have to be the same. Similarity, it's not necessarily that all the parts have to be same. They can be different, but they have to be proportional. Okay. For example, human beings are all similar to each other. They're not perfectly congruent, right? We all have different heights, body shapes, whatnot, but we are similar in many respects. Okay. So again, similarity is not congruency. All right, so definitions. Similarity transformation is a transformation in which an image has the same shape as its pre-image. So if you, for example, if you have a right triangle, okay, and you do some kind of transformation with it, it'll be still some kind of right triangle, okay? So it's not like you're gonna, transform a circle and then it turns into, a dish plate or not a dish plate, like a coffee cup. You're not going to, transform a coffee cup and then it magically turns into a book or a fire monster. Okay, it just doesn't work that way. All right, so if you let's say translate, for example, that right triangle, it's still a right triangle. All right, so similarity transformations include reflections. So if I was to reflect um, this triangle right here, it would still be a right triangle after I reflect it across whatever line of reflection I choose. Okay, so that's a good example. The proof, okay, again, this is the rule actually. Um, for example, if I was to reflect over I believe this is the y-axis, okay, you would notice that the x negate um, when you do that. So I'm just kind of harkening back from what we already learned. So axis, wow. And then the other rule right here is when it reflects across the x-axis because all your y values negate, right? As opposed to the y-axis where the x negate. All right, translations. So if I was just, and I already did an example here, if I was to move that uh, right triangle, it's still going to be a right triangle. Okay, and that's the rule again. Good little, we add or subtract on the x, add or subtract on the y, and that's the rule. Okay, so again, please write these down. It's good for you guys to remind yourselves on what we already learned. All right, rotations. So if I was to rotate, say I rotate this right triangle, if I rotate it 90 degrees, it's still going to be a right triangle by 90 degrees. Okay, it'll still be similar. And again, here's the rule. That's for the rotation of 180 degrees. Remember, both the x and y negate. Okay, so that's an example. Dilations, okay, and we already covered that in 11.1. All right, so in 11.1 we talked about dilations, and remember, here's the simplest rule for on the Cartesian plane. You just have to multiply by your scale factor to your x and your y values for your original pre-image point, and then you get your new image point. Okay, remember k represents a scale factor. All right, so two plane figures are similar if and only if, okay, one figure can be mapped to the other through one or more similar transformations. So again, if you an example of it not being that way would be like um, here's a right triangle, okay, and basically what happens is we go through a couple transformations, and then out comes a circle. Something definitely went wrong. Okay, that's not similar. Those are not similar. Okay, so if we were to write similarity, there's actually a symbol that we use. It's kind of like congruency, but not exactly. Um, it'd be this wavy line, but since these are not similar, I would cross it out. Not similar. Okay. Two right triangles, on the other hand, here's this right triangle, would be similar to the other right triangle. Okay, so similarity is that little squiggle line. So if you ever see me do that, that means similar. All right, so example one, identify the preimage and image. Okay, so first things first, if you look here at the graph, it looks like ABC, right? The blue triangle is definitely going to be your preimage, while A prime, B prime, and C prime, the red triangle, is your image. Okay, it's always important to know which one comes first and which way you could be going. Sometimes you can go backwards, so be aware of a question like that. All right, so what transformation was used for ABC to map onto ABC, A prime, B prime, C prime? Okay, so we had a blue triangle, then we got smaller, right? So if you actually notice the distance here from A to the center of uh, dilation, O, okay, at 0, 0, you would notice that it actually comes in closer, okay? And it actually comes in by half the distance. Same thing with B to B prime, all right? It actually goes closer, okay, it goes in, so it's getting smaller, so that means K is definitely a fraction, right? But it looks like it goes by a half also. And same thing with C, and in fact, you can actually do this. You can go from C to O, and you realize that originally was 6 distance, but now C prime, okay, C prime is only 3. So it looks like our scale factor exists here. So we have a dilation, right? When things get bigger or smaller, we're talking about dilation with the scale factor of K, and it looks like it shrank by 1/2, okay? Now, are A, B, C, and A prime, B prime, C prime similar? Yes. If you actually notice, all your line segments are parallel, right? So visually, they look pretty stunning, right? And it looks like all the line segments follow the same scale factor. So yes, ABC would be similar, squiggly line, to A prime, B prime, C prime, all right? Since um, the dilation uh, with same or constant scale factor, and that was of 1/2. So of 1/2. There we go. Okay, and they look identical. If you look at them, you're like, that's pretty. Those two triangles look very closely identical to each other. Just one's a little bit smaller. All right. Example two. Identify the preimage and image. Again, if we're looking here, notice the notation. We got A, B, C, D. Looks like A, B, C, D is the original, right? And the original is known as the preimage. Okay, and then your image is your new image after you do the transformation, which looks like it's A prime, B prime, C prime, and D prime. All right, what transformation was used for ABCD to map onto A prime, B prime, C prime, D prime? Okay, this is where we can actually show that these two objects are not similar. If you notice the ratio, the distance from AB is 2, as is DC, it's a rectangle. AD is 4 and BC is 4. So those are the dimensions for that rectangle, right? And if you notice, our dimensions here are different. Now, it looks like, notice how B, right, is the closest point to the vertex, and it's still for B prime the closest to the vertex. Looks like we actually did a rotation of 180 degrees. Okay, it looks like we rotated 180 degrees. So this was a rotation at 180 degrees. Um, but if you notice, distance was not preserved. That the sides do not match up. They aren't congruent. All right. So something changed. All right. So are A, B, and C and A prime, B prime, C prime, D prime similar? No, they are not. So A, B, C, D. Okay. Oops. Go back too far. A, B, C, D is not similar. Why? Because, I mean, yes, you're like, Mr. Webb, they're both rectangles. And I agree with you on that, but their proportions are not the same. Okay? What I mean by that is if you actually set it up in a proportional statement, what would happen is notice AB is 2, right? And AD is 4. Now, if we use the same proportionality, and I'm using this side with this side right here, okay? If I use the same proportionality and set it equal to the proportions of this triangle, 3 by 4, they would not be equal to each other. They're not proportional. So since um, not proportional. Okay, so proportionality must be maintained. Otherwise, we're dealing with two completely different types of rectangles. They have nothing to do with each other. All right. Now, if one of them was a little bit smaller, but it had the same ratio, like 1 by 2, it would work perfectly with ABCD. Okay, so if it was something like this, it's like, oh yeah, that's just a dilation, still has the same ratio, okay, because 1 by 2 would be equal to 2 divided by 4 because 2 divided by 4 can be reduced into 1/2. So that would work, but that's not what they gave us. So no, A prime, B prime, C prime, D prime is not similar to A, B, C, D because they're not proportional. Something changed. All right, example 3. So for example 3, identify the pre-image and image. So it looks like our original image, again, looks like A, B, C, D. So that's our pre-image. In fact, let me just do that. There we go. So our pre-image is again A, B, C, D. And our new image is the primes. Okay. So what transformation was used for ABCD to map onto A prime, B prime, C prime, D prime? If you notice, things got bigger, right? From the blue guy to the red guy, things got way bigger. Now, it looks like if you were to put a projector, a light source right here, center of dilation, it looks like it would project this way, right? Same thing with B, projects outward. Okay, just like a projector, does the same type of thing. Okay. There we go. So we have that projector effect, and it looks like if you line up all the lines, you can use your ruler, and your ruler would actually get this coordinate here. And next thing you know, that is your center of dilation. So we definitely have a dilation. Now, by what scale factor? Let's find out. So the distance from A to your center of dilation was 1 diagonal, but now it's 2. So we multiplied. Okay, it looks like we multiplied by 2. You can double check. You can also check the sides. Originally you had 3, for your sides there and 2 here. And now you have 4 and then you have 6, 6 and again 4. So it definitely looks like we multiplied by a scale factor of 2. So that's another way of thinking about it, but both ideas work just fine. So 3 times 2, 6, 2 times 2 gets you the 4. So definitely scale factor of 2. All right. Now, are they similar? Explain. So again, let me clean this up a little bit. Okay, let me try to keep the dimensions there. Okay, there we go. All right. So if we keep the dimensions, all right, we have 2 to the 4, right? So the blue guy was 2 by 3, right? So 2 by 3. And then the red guy was 4 by 6. So 4 by 6. Now, if we actually reduce 4 by 6, it's 2/3. Okay? So yes, these are proportional because they're equal to each other. Their proportions are equal to one another. So 2 over 3 is 2 over 3. They're both 2 over 3s, okay? So yes, A, B, C, D would be similar to A prime, B prime, C prime, and D prime, okay? Because they're proportional. So that's something to note. All right, so your turn. Identify the pre-image and image, just like the other examples. What transformation was used for A, B, C to map onto A prime, B prime, C prime? If you can't find one or think of one, well, that's fine. Um, if you think it's one of them, just try. But then next thing you know, look at the next question. Are these two triangles similar? And then explain. Okay. All right, same thing here. Your turn number 2. Identify the pre-image and image. Identify the transformation that was used. And then after that, are they similar? And then make sure you explain, okay? If there is a rotation or something like that, or translation, give me the actual rule. If it's a dilation, give me the scale factor, okay? All right, fun fact. Okay, so all circles are similar by the circle similarity theorem because all circles have a radius, they all have a diameter, and they all have that same ratio. And guess what that ratio is called? Pi. Okay, they all share that same ratio, so that's why circles are all similar to each other. All right, so main questions again: what kind of transformations result in similar figures? Go ahead and list them. Okay, again, just kind of do a recall off the top of your head. We saw some of them in the examples. Now, last question: are dilations the only transformations that result in an image that is similar to the pre-image? Explain. So, are there other transformations that would maintain similarity? Okay, and this is how I feel a lot of times. I actually done this with my daughter before, where it's like, no, put your feet on the ground, and then they stop freaking out. I feel like this actually explains like teachers too. Like, kids freak out and it's like, no, 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 put your feet on the ground and they just stop, freaking out. Yeah. It's a good job. It's fun.